So welcome everybody to a special lecture, which we are calling the Bourgain Lecture. I want to explain the background for this. It's the first ever given. The Salem Prize was introduced by the Salem family in connection with Salem's work in harmonic analysis and neighbor theory. It became broader in its definition and became a very prestigious prize. The first chair of the prize was Bourgain, and over the years it was run from Paris. But at some point, Bourgain became the chair of this prize committee, and he brought it here. And each year he would choose a committee, and a Salem Prize winner would be chosen. And many well-known people, including some in the audience, have been winners of this prize. And Bourgain's idea of this was the way the prize winner would be rewarded is they come and spend a month here, and he talks to them and maybe writes a paper, which was, I think, very good for him and for many people that had pleasure of working with him. When Bourgain was quite ill and stepped down from his position, he asked me to try recruit, and he was also involved in this, Terry Towers, the next chair of the Salem Prize for some number of years, which Terry Towers agreed, but unfortunately Bourgain passed away just before COVID, and we did nothing for a while, and there was no prize given for a while. But once things started to get back to normal, we approached Tao, and he graciously agreed to be the chair for some number of years. And in the tradition of what Bourgain was doing, and the Salem family is no longer involved in this at all, the Institute has inherited this prize in some form, where the winners, going forward, at least in the near future, will be invited to, if they like, to spend a month here and to give a lecture. And that's what's happened here. So in 2023, after a period of no prize being given for a few years, 2 prizes were given, and the winners were Sarah Pavus, who had been here and has been here many times, and unfortunately we did not take advantage of making her give a lecture last time, so you'll be the first. And the other winner was Julian Sahasrabudhe. Good? Close enough. I've been practicing all day. Who was the other winner, and I'll cite a little bit what the prize for his work on flat polynomials, random matrix theory, and Ramsey theory. So we are very honored to have Julian here for a few weeks according to the new rules, and we thought that we would call it the Bourgain Lecture to honor Bourgain, to remember Bourgain. There's no, you got a lecture here, and if it's got any analysis in it, Bourgain's name will be up on the board anyway in 2 minutes, but it's nice to have a lecture named after him. And this will be the going forward. And this year's lecture, the very first, will be given by Julian. I won't try that again. And the title is The Ramsey Numbers, New Results and Perspective. Thank you.
Thanks so much for that introduction. I've certainly been enjoying my month here. Perhaps somewhat naively, I didn't know what to expect coming here, but I've really enjoyed of course, the mathematics, but also the culture here. I've learned a lot in both respects. So I'll take quite a bit back with me across the Atlantic. Okay, so I'd like to talk today about the Ramsey numbers. And one of my goals here today is to so I'll talk about some new results and some things which I find quite exciting in the field. But I'd also like to motivate the interest in the Ramsey numbers. I think a lot of us are familiar with these Ramsey theoretic concepts, this idea that large objects have some sort of structure in them. But here I really am interested in the quantitative aspects, really like how large do things need to be before we have this sort of phenomenon. I mean, you might say sort of cynically that, oh, who cares about the quantitative aspects? Who cares about these specific values? But I'd like to sort of argue, or at least point out to you, that there's some really interesting mathematics at these different, with this sort of the different sort of growths of these functions. They can sort of mean very different things. And understanding them, I mean, beyond this has led to some, I'll hope to convince you, some very interesting mathematics. Okay, so that out of the way, I'm going to start with, in some sense, the stupidest, sort of silly little example, but it will really get us going. So many of you have seen it before, but let's start at the beginning. And this is really where Ramsey theory starts for us. So if I have a graph on 6 vertices, and I color every edge between them with one of two colors, either red or blue. So I'm going to color every red or blue. No matter how I color them, I can find a monochromatic triangle. So 3 points, which all the connections are red, or all connections are blue. Okay, so in some sense, this is some little stupidity, but it really does lead to some serious mathematics. Okay, so here we go. Let's prove this. So I have 6 points. Let's take some vertex x. Okay, so now there's 5 more points. There has to be 3 of these points that are joined in the same color to x by pigeonhole. Okay, so let's say there's these 3 points joined in red. Okay, good. Now, let's look at each of these pairs. If any of these pairs are red, then we're done. There's my triangle. So each pair better be blue, and we have a triangle in blue. Okay, so this is some sort of silly exercise. But what's really interesting here is that this phenomena persists when we go from 3 to larger numbers. Oh, sorry, let me make one more small observation, is that 6 is actually the best possible. So I could take something like this. So this coloring here has no monochromatic triangles. Okay, so 6 is best possible. Okay, but interestingly, so for 4, if I want to find 4 points that are all connected in the same color, so this, or its red variant, it turns out I need to put down 18 points and ask you to color them. Actually, this 18 is best possible. There exists some sort of very non-trivial color on 17 points for which you avoid any monochromatic. And in general, for any number k, there exists a large enough r of k, so some function of k, so that if I put down r of k points and ask you to color all the connections, I'll find k points. So for any k, there exists some r of k, so that I can find k points with all connections in the same color. And this is some interesting mathematics and goes back to the work of Frank Ramsey, who discovered this fact, who proved this fact that the Ramsey numbers are always finite. Okay, so I've said what this is. Let me just write it on the board. It'll be useful in the future. It'll also be good to introduce some notation. So it's the smallest number n such that every red-blue coloring of Kn. So this is the complete graph on n vertices. This is n points with all possible pairs. I'll use this notation quite a bit, so I'm going to trick you into learning it. Contains a monochromatic k sub k. And what this proves here is r of 3 is equal to 6. And I told you, but did not prove, that r of k is 18. And already, interestingly, r of 5 is not known. There are some bounds which I forget. So I said our main interest here is quantitative. So what is our real question here? What is the growth of these Ramsey numbers? And not so much for small values, but as k is tending to infinity. This is really our main question. So Ramsey actually did give an explicit bound, but really the story gets going in the quantitative sense a few years later. The words of Erdős and Szekérys. So this is 1935. I didn't give this a date, but it is 1930. we showed that R of k is at most 4 to the k. In fact, they did something a little better, but I'll get to that later. Okay, so what's the proof? It's actually just a simple generalization of this idea that we saw for R of 3. So it's useful here to sketch it for what we're going to do later. So what I'm going to do is the following. I'm going to take my entire graph here to start. Here's my x. Okay. And I'm going to be searching for this case of k as follows. So I'm going to look in my world here. I'm going to take a vertex, pluck it outside, and now this vertex is joined to the rest of the world in 2 colors, right? So there'll be some guys that are red and some guys that are blue. One of these will be at least 50%. So what I'm going to do is now shrink my x to the whichever one is larger. And I'm going to put this vertex into some collection of vertices that I've been building up. Or a blue collection here. And just to state it in full, I'm going to, as time goes along, I'm going to have a reservoir here. I'm going to have a fistful of red vertices here, joined to everything here. A fistful of blue vertices here. So everything here is joined in blue, everything here is joined in red and joined here. And every step I just take a vertex, is joined in 50% with the rest in one color, shrink to the larger color, and put that vertex in whichever of these. Okay, so what's the quantitative result now? In each one of these steps, I shrink my world by a factor of 2, basically. Okay. Now, when do I get to stop? Well, when I put k vertices into one of these pockets here, right? Because if I have k vertices here, everything is joined in red, I'm done. Okay, so I know I have to keep going if there's k minus 1 vertices here. Sorry, so I started with, say, n vertices. And I know that I have at most k vertices here because I can only stop if I put k vertices here. So I have k, I'll just say k, but that one with the minus 1. And I need to make sure that in this process, I didn't run out of vertices. I could have just completely killed n. So this always has to be at least 1, and I get the upper bound of 4 to the k. So if n is bigger than 4 to the k, this process will actually work, and we're done. Okay, so in some sense, this is just, I've just written down exactly the same idea that we applied in this first case, but in a slightly more general form. Right, so nothing happened. Now I'm going to do this. So any questions about that? We're just walking along, having the world each time. Okay. Okay, so this is some upper bound, but before I can really start talking about quantitative results, I need to give you some lower bound to show what the situation is. If you sort of play around with it a little bit, you'll sort of think of the following construction. So what are we trying to do? We're trying to find a coloring of a graph, sort of as big as possible, that has no monochromatic clique of size k. So a first idea might be the following. I could have thick little blobs of size, each one of size k minus 1. And color each one of these blobs entirely red. And then put in between all the blobs, everything blue. Now, if the number of blobs is at most k minus 1, now I claim that there's no complete graph on k vertices. Because if it was red, well, it'd have to be entirely inside one of these. They have size at most k minus 1. If it was in blue, it would have to be in different parts, but there's only k minus 1 parts. So what does this say? This is sort of a first lower bound on the Ramsey numbers. That R of k is at least k minus 1 squared. So I think in the olden days, this was quite a convincing type argument, and people actually thought that maybe polynomial was like the right type of size for this number. It should be, but this was a very crude argument here. I'm not really seeing much of the graph. I'm just sort of doing something greedy. Okay, probably this is some sort of structure that's behind it. So this is what was quite shocking. You know, it was shocking to some at the time when Erdős proved the following exponential lower of the Ramsey numbers here. And what's interesting about this is it actually is one of the very first examples, and certainly one of the very first influential examples of the probabilistic method in combinatorics. So what's the proof? In some sense, is the stupidest idea possible. Just take a random coloring. Okay, so let's just prove it right now. So proof. So let n be 2 to the k over 2 or whatever. And now take a random red-blue coloring of the complete graph, where I just choose the color 50-50 independently, all the pairs. So each edge, red / blue with prob 1/2 and independent. Great. So I want to show that the probability, and to finish, I just want to show that the probability that there exists a mono set of size k. Right, so there exists some set where all the edges get colored the same color, is less than 1. Because if this is less than 1, there better be a graph in that collection that actually has everything not monochromatic. Okay, so here what I can do is this is a big union of n choose k events, right, for each possible set. And now each set, well, what's the probability? Fix one of these sets with the probability that all those edges got colored the same color. That's just 2 to the minus k choose 2. Technically +1 because it could be all red or all blue. Okay, done. And now it's just a matter of remembering how to do mathematics, and I claim that this is less than 1. Okay, so I'll just do it for you because just to see. So that's n choose k. So that's k. Okay, so 2. Okay, so here we see what's happening is n is smaller than 2 to the k over 2. This n is getting crushed by this 2 to the minus k over 2, blah, 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 less than 1. Therefore, this is less than 1. Therefore, there exists an example. Okay. So actually, so this is a very nice example in that actually I've given you a probabilistic proof of existence in 2 seconds. It's actually not known how to construct these at all, right? So even getting an exponential lower bound via some kind of constructive means is something we don't know how to do at the moment. Okay, so what do we have? Let's collect our thoughts here. Oh, sorry, let me make one more remark here. So if you do this calculation a little bit more carefully, you get this is at least 1 plus little of 1 as k tends to infinity times 1 over 2, root 2 e, k. So I just put in the lower order terms here. If you do this analysis carefully, interestingly, the only improvement in all these years since, so this was, I didn't tell you the date, this was 47. The only improvement is that this 2 is now moved upstairs. So it's a factor of 2 in all these years. So this is really tough to improve. And honestly, at this point, just putting like a 1 plus epsilon seems to be like a fixed epsilon at this point. It seems already to be interesting.
I assume, let's believe this is the order of magnitude.
Okay, so yeah, I'll say something about this in a minute. Okay. Oh, sorry, just one more remark here, which will be useful later. So this is actually the correct, if you want to do a random coloring, we only proved a one-sided bound, but this is actually the correct answer for random. So if you go a little bit bigger than this amount, then a random graph will have lots of cliques of size k. So this is sort of, but we understand everything about random here are the cliques in the random graph, and we have since like at least the 80s, certainly. Okay, so let's take stock. R of k is at most 4 to the k. This is Erdős-Steckers. And it's basically 2 to the k over 2. Okay, so we know that it's exponential. We have an exponential upper bound, lower bound, and so on. But what's going on between these bounds? And this is really where the content of this talk starts. Okay, and now I'd like to just sort of point my finger a little bit here at, we can already start to see the kind of meaning between these different possible values here. So let me say something about this. So let's consider possible different worlds that we could live in. Okay, so if R of k is, say, something like 2 to the k over 2, this means basically, so this is not a mathematical statement. This is a possible different worlds, different world statements. Okay, so if we live in this world where R of k is 2 to the k over 2, this means that random is really the best thing for this kind of coloring. And there's actually some like subtle things if you really start digging what's happening with the random graph. It would be like, extremely fascinating if you can't beat this. Okay, let's go to the other stream. I'll say one more word about that in a second. Well, what if R of k is something like 4 to the k? Well, let's go back to this argument we had up here. So this was tight for 4 to the k. I mean, it's what gave us 4 to the k. But what was sort of, what would have to happen if this was really the truth? Well, we're walking along, taking a red step or a blue step, shrinking our worlds at each time. If 4 to the k were the truth, our enemy would have to somehow force us to take a red step, maybe take a few red steps, and then take a few blue steps, then take a few red steps, and take a few blue steps, or something like this. So what this is kind of saying, in fact, you could even say your enemy takes like, force you to take like little o k red steps, and then you're like now in this very small part of the world, you look around, and then for some reason, you have to start taking blue steps. So something here, if this was the truth, this sort of means that there exists graphs where the microscopic structure does not communicate with the macroscopic. Right, so I take a bunch of steps, and now I've sort of lost all the information about what was happening in that earlier steps. I couldn't sort of steer my process at all. Oh, I didn't write anything, so this is also bad. So there's a third opportunity that people often consider, which is, and it's sort of a natural point, which is, what if it's like 2 to the k? What would this mean? And this is really interesting, and we can, again, understand it from this perspective. So what was sort of wasteful about this algorithm, as we saw, is I was having to pay, even if I built a red clique at the end, I was having to pay for building this potential blue clique. What I'd like to say is, look at my graph and say, look, no, what I can do is take red steps all the way down, right? So if I could guarantee you that I'm always taking red steps, I would only be losing this factor of 2 k times. So now my algorithm would bottom out when this is like 1, okay, and then I get an next 2 to the k. In fact, this is what would happen if you apply this algorithm to the random graph. For example, the gn 1/2, then everything's always intersecting in about 50%. And you would get an upper bound of 2 to the k. But now if this is really equal to 2 to the k, that would mean that there exist these graphs that are like random graphs in their neighborhood intersections, but they're sort of more random-like than random graphs because they don't have these other sort of small fluctuations that give you these cliques much earlier. So if this is true, there exist graphs that are much more regular. This is about neighborhood intersections than random. Okay. Is there any questions actually at this point?
Could I ask something?
Yes.
If I give you a random graph on n vertices and you want to algorithmically find a clique, do you know what you should expect? Is it like log base 2 of n or something?
Yeah, exactly. So basically this 2 to the k is the best thing we know. Beating that by, so we know that there exist bigger cliques in there, but finding them we don't have any idea how to find them. This is a very interesting question. Yeah, like there's even like a more like sort of rude way to ask this question. Just write down any property that you want GMP to satisfy. Just give me anything that's sort of reasonable. That doesn't just immediately give you the answer. And say, okay, now forget the randomness, just prove it using those properties.
Let me ask a question. I assume that in the random model of fluctuations are tiny so that you don't get unusual outliers. You might hope that the variance were big so that you would have, but I assume that when k goes, when you get larger, these things all conflate on the mean very sharply. Is that right?
Exactly. Yeah. So actually in GM1/2, for example, the clique number is, or the clique number is concentrated on a single value.
Yeah.
So we have this like very sharp concentration. But finding that is really a needle in the haystack.
Yeah.
If you just give me the graph and ask to find it, it seems extremely hard. In fact, even pushing below this 2 to the k, already you're in serious needle in the haystack type territory. Okay, so what is known about these Ramsey numbers? So I told you results from the 30s and a result from the 40s. What has happened since? So, actually, Ernest Sakharich proved a slightly better bound. It's just you analyze this algorithm a little bit more carefully using sort of an induction. And then this was improved by Rödel in the 80s by an extra polylog factor, by Thomason and by a polynomial factor. This is again in the 80s. That's by Conlon, who improved it by a growing polynomial, something growing faster than any polynomial. So that's right. So this is log k of 1. This is Conlon. And then fairly recently, like in 23, Saab removed this little o wall here. Okay, so these are not improving this 4 here, but there's actually a lot of really important ideas in this line of work. So even already in this paper of Rödel, there's some very nice ideas, and this is sort of actually the beginning of quasi-randomness inside of graph theory. So Thomason introduced a notion of quasi-randomness to do this step much better, which was then developed by Conlon and Saw in more recently. Okay, so wow. Okay, so a few years ago, last year.
We expect it's after 23.
Yeah, exactly. myself with Marcelo Campos, Simon Griffiths, Rob Morris, and myself, we obtained the first exponential improvement to the diagonal Ramsey number. So 4 minus c, okay. So there exists some c bigger than 0, such that we have the following. So, okay, so this is the first time the bound is moved since the original work of Ernst Seckerish. So, but I thought I would do, I did this the other day and I kind of liked it. So, but let me sort of state my reservations about this result. So I'm gonna put a good category and a bad category. Okay, so on the one hand, we feel happy because, okay, so we improved the Ramsey number, it's good. Right? But there was several less satisfying aspects of this proof. So one, which is it didn't naturally generalize to the multicolor version of the problem. So no and I'll say what that is in a second. Should have said known improvement. To multicolor version of the problem. Okay, so here we've been coloring with red and blue. What's wrong with coloring with red, blue, and green? Right, very natural question. And curiously, the two color problems in Ramsey theory seems to be like slightly, they seem to be slightly special in some way. It's not unusual that something will be first proved for the two color, and then there'll be some really significant hurdles to overcome to get to the multicolor version. So somehow there was something special about two colors for argument, and that's not particularly satisfying. Another odd thing is, and I'll come to this later in the talk, is we had this, the way we were thinking about approaching this was really motivated by these sort of intuitions and problems that we had in geometry, or sort of questions about random variables taking values in high dimension. But in the end, we sort of got around that and didn't really see that connection in the proof. So did not see this connection with, I'll just say geometry, but really random variables in high dimension. And the final is, well, a little bit more touchy-feely. So I don't know. I mean, perhaps we all feel like we deserve our success. And if you look at our proof, there's something that looks a little bit lucky about it. So in the way we actually approach this problem is we first attack what are known as like the off-diagonal Ramsey numbers. I won't define them here, but is the off-diagonal Ramsey numbers. And then what we do is we relate the diagonal Ramsey numbers to the off-diagonal Ramsey numbers using a different argument. And this one argument we use to relate the two is actually lossy. So we're like losing against Erdős-Szekerish, but then we can get it all the way down to the off-diagonal. And then our algorithm is winning enough on the off-diagonal that it makes up for the loss and it gets the exponential win. But this is a bit unsatisfying, is that there's these two competing forces and it doesn't really seem obvious why it should work. So we sort of want some kind of proof that makes it more obvious that this approach is really motivated and sort of should work.
I have another question. So in the sphere packing analog problem,
Yeah.
upper bound linear program methods are very powerful.
Right, yeah.
There's no linear program approach to this upper bound.
Not that I know of. Yeah, I think this is an interesting question now. Yeah. So, what? I should say that,
Are you saying that all these other ones that you just erased do apply to the multicolor version?
this is a great question. So actually, as far as we can tell, none of them apply to the multicolored version.
So this unsmiley face should really apply to the entire field, not just.
Yeah, exactly. It's a weight we carry, indeed, yeah. Yeah, in fact, even this like log improvement by Rodel seems to be, it definitely uses a tool that's fundamentally two colors. So we don't know any way by any means to improve the multicolor. Okay, so we proved this last spring. And this spring we got together and was trying to kind of like rehash and try to re-understand what we were doing and try to maybe try to reinvent some of the steps and hopefully answer some of these questions. So actually, this is what I'm going to announce here is the following. So the theorem, so it's this same group. And we got and sort of workshopped our approach with a bunch of sort of familiar faces to us. So Paul Ballister, Bela Bosch, Johan Hurley, and Marius Tiba. And with this, we are able to improve, I'll just say it in words first. So an exponential improvement for the multicolor diagonal Ramsey numbers. Improvement for multicolor diagonals. I can actually say that our old proof actually works amazingly on the off diagonal. So it also applied naturally to the off diagonal, by getting the sort of most natural, most basic one we didn't know how to do. Okay, so what does this mean? So for every number of colors, there exists some delta such that R sub R, okay, so this is, now you're allowed to color with R colors, is at most, so this is the exponential improvement. Okay, exponential improvement over what? Okay, so what do I put here? This is R to the R times K here. So where does this come? This actually comes from the same basic argument that I told you at the beginning, but now instead of splitting it into two sets at every stage, I split it into R sets, right? So that's where we're getting this, this R here. And now we have these R different groups we all have we're putting vertices into, and that's giving us this R to here. So this is R to the R over K. And that's what we have. Okay, so this deals with our first bit of sadness over here. Interestingly, we also, in doing this, make this actual sort of more explicit connection to geometry here. So I'll try to say something about that. And it wasn't actually our original approach, it's a different approach that we sort of rehashed a little bit later. And also this proof also works just as well for two colors. And now we don't have to do any of this weird business when we're going to the off diagonal and running at a loss and then gaining a win. We can just sort of immediately see on the diagonal. So hopefully this is a better motivated proof. Certainly we feel better about it.
Sorry, is it so complicated to say what the diagonal of diagonal is?
Sure, yeah, I can just do it. Yeah, so I can define RLK to be the minimum n such that every two coloring of the complete graph on n vertices now either has a monochromatic blue, sorry, a blue K-sub-L, a blue K-sub-L, or a red K-sub-K.
So R's KK is your other RK.
Exactly, yeah. So yeah, exactly. So this is this business And for example, our algorithm, our original algorithm runs brilliantly when you're looking at things like this, or even more off diagonal. In fact, you can push it closer, but like this is, yeah, very low. So we're trying to have something natural that stays on the diagonal. Okay. That clock work? It does. Right. So I didn't say anything about the history here of the multicolor diagonal. So as Raymond inquired about, this is actually, as far as we know, the original Erdős-Separish bound is all that's known for the upper bound. So I don't know if there's some sort of folklore understanding out there, but we're not aware. So even improving, getting a little low here is out front is certainly not published. So lower bound is actually an interesting story what's happening with the lower bound. So it turns out no longer random is best here. And it turns out better to do some kind of like product type construction. And the best known bounds give something like c to the k. And there's been like a series of improvements on this. So Lefman in the 70s gave the first construction that, just sort of really an observation, that gave the first construction that beat random. But recently there's been some clever constructions improving this constant. So Conlon Ferber just a few years ago, and this was also improved by Victorson the younger, and also Wilson. Okay, so as R is growing, this gap is actually growing as well. And you might hope that our delta would be growing as R grows, but this is not the case.
Right. C, how does it depend on R?
No, it's just bounded above. Yeah. Yeah. So it'd be very interesting to get something that grows with R. Yeah, exactly. So this is the little history lesson. Good. Okay, so how much time do I have here? When did we start? Okay. Okay, so for the remainder of the talk, I'd like to sketch the new ideas that go into this proof. Actually, so maybe it's a good moment just to pause if there's any questions.
You might answer this, so talking about this proof, but is this C computable?
The C that comes from our proof, certainly, yeah. And there's also been an improvement. So the best known bound at the moment, is like something like 3.8 to the K. It's been optimized and sort of new ideas, and it's so long way from 2, even getting something like 3 seems to be, to me, feels quite far off at the moment. Seems to be quite a few new ideas.
So Julian, you evaded Peter's question about what you believe the right answer.
Yeah, you seem to be saying 2 to the K now, really?
Okay, so
Random
The two classics.
okay.
But
This is actually an interesting experience for me because after this business, people would often ask the question, right? What do you believe the answer is? Right? So, and I often just said square root 2 to the K because random is best. Why not? It just seems like the even beating it by a tiny bit's extremely hard. But I don't know. I have to admit it's an extremely naive view. I think that proving that it's at most 2 to the K is like seems very hard but possible. But as soon as you start to go below 2 to the K, I have like sort of completely lost intuition actually what's happening. So there's even like simpler problems that take away some of the difficulties of the diagonal Ramsey numbers, but pushing below the analog of 2 to the K is like very mysterious. So it's almost like 2 different problems, I think, getting to 2 to the K and then seeing or understanding anything what's happening between random and 2 to the K. So root 2 to the K, 2 to the K. So I think I would naively guess 2 to the k, but, sorry, root 2 to the k, but I really don't know. I have to say, a lot of people in the community do not believe root 2 to the k, which I thought was surprising, but I only found this out. Good, okay. So, like our original proof, the idea was to construct these objects called books. But before I come to it, let's just think a little bit about, and I've already said it before, the Erdős-Szekers proof. So the problem was in Erdős-Szekers is one source of inefficiency is you're having to alternate colors. We're taking a red vertex, we're taking a blue vertex, and now I'm having to pay for both. What we'd like to do is look at our graph and say, great, we should really go for red vertices. Right? So I'd like to say I can take quite a few, maybe like constant times k, red steps all in a row, for example. If you can do this somewhat efficiently, you can already sort of argue that you get an improvement on the diagonal Ramsey numbers. So if I just draw this as a graph, I get what's called a book. Okay, so here's a red book. So I'm trying to create an object like this. So all of these vertices have the same color red. So that's T. And all these vertices are joined to everything here in the color red. And I don't know anything about the coloring here. So this is the same as sort of putting these T vertices into one of my 2 sets here. So this is a book.
T are also connected to each other.
So
The T upstairs are also connected to each other.
yeah, so everything here is it's a partial clique. And now to put more vertices in my clique, I'm going to work down here. So in particular, I'd like to run this for a long time, where T is like constant times k. And here we actually want like a small constant. And we're going to apply Ramsey inside of here. So say I can certify to you that this bit here is bigger than the Ramsey number. Oh, it's actually good I define the off diagonals here for this moment, right? So I've already sort of put a bunch of guys into my red clique. So if this guy is bigger than this, then I'll either find a blue case of k here, or find a red k minus t down here, and then I can add this and I have it. So, but all it is really sort of forcing yourself, trying to get the process to take a bunch of red steps in a row, and really quite a few. Right, so that our world is shrinking actually by an exponential amount. Okay, so now what I'd like to do is like sort of sketch out the general setup of the problem. So so this is a bit similar to our original, but what we're going to do is actually split the 2 books. So actually, instead of creating one book, so we have this sort of asymmetric construction here, where we're just constructing one red book. But now we're going to try to construct a red book and a blue book simultaneously. Okay, so here we have a set X. Okay, so I'm just going to draw a little bit and then partly for oops, sorry. Y sub red blue and Y sub red. Yeah, okay. So what's happening? So this here is going to be the partial. So this is the picture, and what I'm drawing here is the picture that I'm going to maintain throughout the argument. And I just want to sketch a little bit here, and then I'll hopefully try to connect to the geometric problem that's really at the heart of making this confusing picture run. So this might be a little bit confusing, but there's sort of a very natural geometric picture that lies underneath all these things. Okay, so here's my red book that I've constructed so far in the running of this algorithm. Here's some blue book that I've constructed so far in the running of this algorithm. And actually, so a bit distinct from our previous thing, these are separate reservoirs. Sorry, these are separate over here. Okay. Now, as the algorithm runs, I'm going to always select vertices from this collection X. So this is our reservoir of potential vertices to put into A or B, just like we had in the Erdos-Sekresh argument. So
You're
what is
not duplicating anything.
Sir?
You're not duplicating anything.
No, no, exactly. So what's happening here is the following. So let's oh, sorry, let me just say before I get to that, is I also am going to want to maintain some good red density between here and here. I want to maintain some good blue density between here and here. Okay, and I sort of want to preserve this picture as time goes on. Okay, so what does it mean? So what is my move? Let's take a vertex. So I'm just going to sort of play with this picture and sort of see what we need, and then we'll get to this geometric problem. So I'm going to take a vertex here and pull it aside. Okay, say this vertex was good to choose. We don't exactly know why, but okay, so now this is joined to some guys here in red and some guys here in blue. For some reason, I swapped the colors here. Great. And what I'd like to do in order to get this algorithm to keep going, okay, say red was quite large here. So what I'd like to do is take this vertex, shrink X to this neighborhood. Now put this vertex into here. And in order to maintain this property, finally, I want to intersect with the neighborhood, the red neighborhood of X, with this Y here. So I shrink this, and now I maintain this picture. Okay, and by symmetry, obviously, I could just do the same thing if this this neighborhood over here was bigger, right? So I could shrink this to blue, put this here, now intersect with the blue neighborhood here, I maintain the picture. Okay. But what's sort of potentially going wrong for us here? And this is where we'll get to the kind of interesting question. Okay. Now, of course, it's really important to maintain that there's lots of red edges between here and here. Otherwise, when I look at this vertex and I look at this neighborhood might be very, very small. And the fact that the blue neighborhood is big is of no use, because here I've committed to building this red structure. Okay, so I really need to maintain red edges here and red edges here. What could go wrong when I take this step? Okay, so I'm shrinking now this set down to this set here. Say I'm taking this red step that I described, and I'm shrinking this guy here down to this here. So it's very possible that while I have lots of red edges between here and here, the density between this bit here and this bit here is dropping by quite a bit. And I should say, this is not just a potential problem. This really can happen. Okay, and it's also possible that this could happen, and the same is happening sort of for this color here. Now, if you look at this picture and think about it for a bit, it seems almost like you should be able to construct a coloring for which this is just, you're totally screwed everywhere. But there's actually a little bit of structure here that we can exploit. So let's take a closer look. So I have this vertex X, and if the density between here and here is low, okay, then a typical vertex here, Y, when I look at its red neighborhood over here, it will be a little bit more repulsed from this intersection than, so I'm just sort of assuming that we know all the degrees here are good, but if I pass out to this set, these two neighborhoods are sort of a little bit more disjoint than they ought to be on average. And when you think about this a little bit, it sort of turns the whole thing into, or at least we like thinking about it, this like a little bit from a geometric perspective. Okay, so for each vertex X in our reservoir, this is a capital X, we associate a vector, or it's actually a pair of vectors, U of X, V of X. where, so these guys are actually going to be living in R to the n. Don't worry about what n is, it's just some sufficiently big number here, doesn't matter too much. Where this guy is going to be encoding this intersection with the red intersection over here. So this is going to be encoding red intersection with y sub red. And this is going to be encoding the intersection of this blue neighborhood over with my blue world down here. So encoding intersection with blue neighborhood. This is neighborhood blue intersection was. Okay, so it's actually a simple translation. All we're doing is just sort of subtracting off the expected the density of edges and then rescaling to get each one of these. But now we have like a nice kind of sort of geometric realization of our bad situation here. So the observation is that, or the definition of these is such that if the neighborhood, the red neighborhood of X intersection the red neighborhood of our Y, so these are two potential points on the left-hand side, intersects, say, the red side in about, so let's write P sub R for like the current red density here. And I'll write sort of P sub blue B for the blue density. And say you're just like a little bit below the density that you expect. And it's like size of. Right, so if I were to delete this epsilon, I mean, it doesn't even matter what this epsilon is, so it's true for all numbers. But say you're a little bit below the density you expect, this will correspond to having ux uy sort of at least minus epsilon here. So I've just sort of thrown away this information. I'm thinking about it in this like nice geometric setting. Okay. And now we see kind of what the problem is here. So we have an X and a Y. What's the problem? So if I want to go into the red neighborhood, the problem would be if all of these guys here are negatively correlated with this guy in this world. And if I go into the blue, almost all of these guys are negatively correlated with the blue world. So here's our little like toy problem here. Okay, so I'm given two sets of points, u x, x and x, and the sort of coupled set of points, v sub x, x and x, both in R to the n. And I say I have the following property. So for all but delta proportion of the pairs, I have the following. So either I have that these guys are pointing in the wrong direction. So US, UY is smaller than minus epsilon, or VX, EY is smaller than minus epsilon. So what does this look like? So I'm going to add one further condition here, but let me sketch first. Okay, so I'll just draw it on a sphere. I didn't say anything about being on a sphere, but say I'm on a sphere just for sake of the picture. I get one collection of points corresponding to these blue neighborhoods, and I get another collection of points corresponding to the red neighborhood. And now let's say I make a graph where I draw an edge between two of these points. If the angle is sort of significantly larger than 90 degrees, right? Significantly coming from this. Okay. What I'm sort of asking here is, can you couple the red points with the blue points? Can you pair them up so that when you take these two graphs and put them on top of each other using this pairing, you cover almost all of the pairs, except, right, so I'm allowing some delta wiggle. And it sort of seems like the answer should be no. There's one way which you can make it to be yes, it seems, which is, okay, what if you just make all the delta proportion of these guys just negative? And this is possible. So, so say for all but this, we have this, then, so this is the problem, show that there exists a, by which I mean, so something you could do is you can say, take these U's, for example, and cluster them around points of a simplex. So that, say this is negative all but delta proportion of the time. Then you just automatically have this. But it turns out this kind of situation is amazing for us. Because if lots of these, like, so if I'm clustered around the points of a simplex, this inner product is going to be large for many values, which means that this intersection is going to be large. So this is going to be like a large plus value here, which means this value is going to be large for many values, which suggests a different sort of step in this kind of picture. Instead of putting anything into your book, either book, you just say, okay, let's not worry about building a book. All I'm going to do is use this to shrink things so that I get a huge density boost between two of these pairs. So yeah, so this is sort of the toy problem. Say you have no collection of pairs that are not too clustered, then you don't have this sort of phenomenon. And this is the new thing that we prove. And this makes for a very nice running of the algorithm. Let me just finish by putting up this statement in the context of two colors. And I'll just say, of course, all this generalizes. The point of this is it generalizes immediately, actually, to more colors. So let me get our new geometric lemma. So we have our two collections of points, u sub x, x and x, and v sub x, x and x. In R to the n. Okay. Then there exists some lambda, which is at least -1, such that, okay, so what am I going to do? I look at two random points, x and y, in x, just chosen uniformly at random. And now I look at the inner product that I'm interested in here. So this is u of x, u sub y is at least lambda u of y, u y. So this is at least e to the minus lambda plus. Okay, so either we have this or we have the same thing with the u's and the y's swapped. So
There's no fee. Where's fee?
that,
It's all used. You don't have the T.
excuse me, sorry. So, okay, so let me just digest what this is saying and see how it's answering this kind of question. If lambda is small, even possibly just -1, what this is saying, for a good proportion of the time, so we have a lower bound here, for a good proportion of the time, both of these coupled pairs are not too negative. Right? So for a nice healthy proportion of these times, we can bound these guys from below. Or the lemma spits out a very large lambda, like for example, in the case of a simplex, and it will have found So in this case, this doesn't really matter as much, but it will have found a bunch of pairs now occurring with like a much smaller probability, but that are very, very correlated. So there's some trade-off between these two numbers here, but they're very correlated. And this is identifying this cap that we were looking for, this sort of clustering. Okay, and this basically corresponds to the two kinds of steps. Either our lambda is very small, we can take a book step. Over here, everything is nice, everything's sort of intersecting how it should. Or this lemma spits out a large lambda, and we found some sort of clustering. Reading this backwards, that corresponds to some potential density increment steps. So we actually can add a lot of edges between two of these pairs, or increase the density quite a bit by passing to a subworld. Okay, so I'll stop there. Thank you very much.
Well, thanks for a wonderful first Bourgain lecture. Beautiful results. I think we have time for a couple of quick questions.
What is the dimension n of your space? How is that?
Yeah, so I just didn't want to, it's actually very simple, the translation. I just didn't want to waste the time doing it. So this u of x is basically just the indicator in this world. So this is just red neighborhood of x minus the density. It's not quite what we do, but divided by this is red density. So intersection y of r times y. So this is just actually the size, the dimension is just the size of y of r. So it's technically shrinking, but it's always at most.
So kind of related. So in this lemma, they are unit vectors, I assume?
They normalize somehow.
So the normalization actually does not matter in this lemma, weirdly. Yeah.
So you scale it, then the
That
probability.
doesn't matter. Really? But they want the sphere there, some.
Yeah, this was just to have a picture, but
But the
scaling is actually not mattering. Yeah.
Really the inner product.
Yeah, exactly.
The scales, how do they depend on the dimension?
The scale.
Do they depend on it?
I mean, here, like just for the statement of the lemma, the scaling doesn't depend on the dimension. Yeah, so there's no. This is just any collection of points in our.
The constant c and lambda do not depend on it.
So lambda is given by the lemma. So
So the universal constants.
So this is just this is given, and this very much depends on what these collections are. So for example, this would be large if these have like they're sort of clustering in some way. If they're just like random, this lambda could just be -1, for example. Yeah, and then there's universal little constants here.
All right, yeah, still two more questions, okay.
Sorry, can you just repeat the second conclusion of the lemma? The second case?
Right, so it's just the u's and the v's are totally symmetric, so it's just the other way around. So here we have vx comma vy is at least lambda, and shakes it in ux uy is at least -1. So and then this thing is at least same bound here.
Why can't you take U to be just the quarters of a simplex with radius 10 and V the same vectors? Then wouldn't this be violated? Because all of them would be in the -10.
But so what you would have is you would have the simplex, and you'd have all these points in the direction of the simplex.
No, I want to take the U axis to be each of them a different corner of a simplex of radius 10. Then all of their inner products will be -10, and this seems to be false.
All of their inner products.
That's not the dimensions, because the angle goes as -1 over n. So for n the dimension of the simplex.
Yeah, but I'm allowed to scale. The point is, I'm allowed to scale them where I want because they're in our ends. You just scale them as large as you want.
I think it's.
The theorem seems false, right? So There must be some scale somewhere, right? Because
Right.
your point, presumably.
Put them on the sphere.
Well, on the sphere, they would probably be very
He
minus
carefully
one.
divided by square root.
He's got a square root.
Yeah.
He's got like a
No,
calculation.
no, that's fine, but the lemma.
I understand.
It's angle.
We all feel less.
Thanks.
I think it's one.
Enormous root n kind of makes sense.
Yeah, so
Yeah.
can you do something about directed? Yeah, okay, this is, yeah, so we should, I don't know, I haven't thought of that at all. Yeah, it's a nice question.
All right, I think Bourgain would have loved the talk. Congratulations.